hydrocarbons. Within hydrocarbons, the physical properties of alkanes. So first we talk about their state, gaseous, liquid or waxy solids. The C1 to C4 means from CH4, that is one carbon, to butane, that is CH3, CH2, CH2, CH3 up to here. These are gases. Then from C5 to C17 means the alkanes having 5 carbons to 17 carbons are liquids, and then higher ones are waxy solids, C18 onwards, waxy solids. Then alkanes have generally low boiling point, and the reason is very simple, because they are non-polar, right? The alkanes are non-polar, so there is no force of attraction due to polarity difference. If there is polarity difference, then it will be some partial positive charge, some partial negative charge in the molecule, and another molecule having partial positive charge, partial negative charge will attract it. Okay, negative and positive will attract. In this case, there is no positive negative, that much difference in electronegativity is not there, so that's why very low boiling point. But having said so, if we keep on increasing the number of carbon atoms, the van der Waals force increase. Van der Waals forces are those forces which are between any two objects. Okay, between any two objects, and in physics you might have done it as force is say some constant here, then m1 m2 divided by r square, means their masses multiplied and their distance, the distance between the centers of those two squared. This is called van der Waals force. So this is not a chemical force, this is just a physical force, van der Waals force. So if we keep on increasing the number of carbon atoms, the force of attraction will increase, because the increase in molecular mass will happen. So if I have CH3, CH2, CH2, okay, so the rough shape might be like this. And if I have another molecule, obviously there will be billions of molecules. If I talk about 1 mole of it, CH3, CH2, CH3, it is CH3 here, then the contact surface area is this much only. So the force of attraction will be on this particular area. But suppose I increase one carbon now, CH3, CH2, CH2, CH3, and another molecule of the same compound, butane, CH3, CH2, CH2, CH3, right? So in this case, the contact surface area is greater, so greater force of attraction. So that's why when we increase the number of carbon atoms in straight chain alkanes, the boiling point will increase. Then the next one, melting point. Remember, boiling point and melting point are different, and the phenomenon is also different. Okay, the reason is boiling point is conversion from liquid to gaseous phase, and in liquids the molecules can rotate, but in melting point the molecules are fixed in solid and then they get converted to liquid. So melting is from solid to liquid. In this case, what happens, that the placement of the molecules matters. Placement, okay, how they fit into the crystal lattice. If you compare it with the boiling point, in boiling point you have liquid and liquid gets converted to gas. When it is liquid, and if the molecule is polar, okay, so in that case there will be force of attraction, polar, right, polar. And even if suppose initially this molecule was not like this, suppose negative were closer, suppose, okay, then there won't be any force of attraction, rather they will repel each other, and they can, because it is liquid, so molecules can go away, and after that this molecule can rotate, and when it rotates, plus comes near to the negative of other molecule and negative goes away. Now there will be force of attraction and they will stay in this situation, okay, unless we apply some force. For example, we heat it to boil, If we don't apply that force, they will stay in this position. So in case of boiling point, polarity matters. However, in case of melting point, that is solid, how effectively they fit, that is the molecules fit in the crystal lattice, that matters. Okay, so it means in solid, symmetry matters. Okay, however, both will have some impact in both cases, whether I am talking about solid to liquid or liquid to gas, both, that is symmetrical or polar, both will have some impact. But in melting point, that is solid to liquid, symmetry will decide, primarily symmetry will decide the melting point. In case of liquid to gaseous, polarity will primarily decide the boiling point. So coming back to melting point now. Melting point of hydrocarbons with odd number of carbon atoms is lower than even ones, because even ones can fit into crystal lattice more readily due to symmetrical structure. So remember, when I am talking about melting point, I will be talking about symmetrical structures, because they will fit perfectly or near to perfection into the crystal lattice. So if I say this one, n-hexane has hexane, means 6 carbons, even numbered, means they are symmetrical. If they are symmetrical, they will fit into crystal lattice perfectly. So they will have higher boiling point. Now if I compare the heptane, heptane will have 7 carbons, odd numbered carbons. Now these molecules will not fit readily in symmetrical manner into the crystal lattice. So they will have lower boiling point, because here if they fit in the crystal lattice, it means the force of attraction will be higher. So they fit readily, higher force of attraction. Higher force of attraction means you will require higher energy to convert them into liquid. So higher melting point. The reverse will be the case for heptane. You just need to remember, for the even numbered, obviously for odd numbered, it will be opposite of that one. Then branched chain hydrocarbons have lower boiling point. This is very important point, and many questions are asked based on this one. Arrange these compounds in increasing order of boiling point, arrange these in decreasing order. And this is very simple if you remember one simple point. Remember, I am talking about here isomeric or almost equal molecular mass compounds. Okay, so this is applicable, this rule is applicable when we have compounds, either those are isomeric, okay, means we suppose I have n-heptane and then I have branches also. So for example, I have 2-methylhexane, so 2-methylhexane and n-heptane will be isomeric. In those cases, this rule will apply. Or even if it is different, they have almost same molecular mass. Then branched chain hydrocarbons will have lower boiling point, and the reason is very simple, what we have talked about earlier also, that if I have, suppose I am taking example of n-heptane, CH3, CH2, 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 CH3, right? 7 carbons, and this will be somewhat linear molecule. Now suppose I bring this one here as side chain. So what will be the case? Now it will be CH3, CH, CH3, CH2, 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 CH3. Still there are 7 carbons. Okay, there are 7 carbons and there will be 16 hydrogens as per the formula of alkane, CnH2n plus 2. But now if you consider the shape is somewhat like this. Now two molecules, such molecules cannot be very close to one another, or in other words, the contact surface area will be less. In first case, if I talk about in first case, the other molecule can be like this, and the contact surface area will be here, contact surface area, very high contact surface area. Okay, but in case of branched chain isomers, so if I consider branched chain isomer, okay, here, in this case, suppose I have another molecule of this one, it will be like this, another molecule. So contact surface area here is less. So if branching increases, the contact surface area decreases, and hence boiling point decreases, because now they don't have greater force of attraction as much as they had when it was flat molecule. So how I will write it? I will say increased branching will lead to lower contact surface area. It will lead to lower force of attraction. It means I will require less energy to separate them, means lower boiling point. I can say boiling point is inversely proportional to branching. If I am increasing the branching, the boiling point is going down. Yeah, so boiling point is inversely proportional to branching. This simple concept you will use in many questions. Okay, whether the questions are direct, this concept asked, or if 4 compounds are given and you are asked arrange these into increasing or decreasing order of boiling point. Now the next one. Hydrocarbons are insoluble in polar solvents because they are non-polar. There is thumb rule which you need to remember, and it will be applicable at various levels at various positions in 12th grade also. So here you will say that polar, that is the thumb rule. Polar compounds dissolve polar solvents. Sorry, polar solutes, not solvent. It means non-polar will dissolve non-polar. So in this case, hydrocarbons are non-polar. We don't have electronegative elements here, only carbon and hydrogen in hydrocarbons. Okay, so in that case, there is no polarity, negligible polarity. So obviously they will not be soluble in polar solvents. Polar solvents means water, for example. So water molecule is polar because the water molecule structure is vent structure, right? So this will be the polarity, this will be the polarity here, and if you break it into vectors, these will be 2 components of the dipole on hydrogen, these will be the 2 components of dipole. Now these 2 will get cancelled, horizontal ones in right and left direction, they will cancel. It means overall there will be polarity in upward direction. So water molecule is polar, it means the hydrocarbons will not be divisible in water, and that's what you see, right? For example, kerosene oil, that's hydrocarbon, mixture of hydrocarbon, it will not get dissolved into water. Okay? So oils, etc., these are hydrocarbons, these are not soluble in water. They are soluble in organic solvents, obviously, okay, like ether and CCl4. Liquid hydrocarbons themselves are good solvent for alkanes. Means, if you remember, we talked about that C1 to C4 are gases, C5 to C17 are liquids, and C18 onwards are solids. So this statement, this particular one, this statement is pointing that these solids will be soluble in these liquids, C5 to C17. So these will act as solvent for solid fluids, and you can mix these liquids as well. So liquid can be mixed in liquid, and you can mix the solutes also in these solvents, liquids. Density of alkanes is proportional to molecular mass. So suppose you have been given similar type of compounds. Okay, so for example, if I am talking about N pentane, CH3, CH2, 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 CH3, and I am talking about N hexane. Okay. So molecular mass obviously here is greater, so they will have higher density. In simple terms, if you have similar structures, okay, and mostly you will get questions on similar structures, right? Otherwise there are various factors which will come into consideration, the contact surface area, etc. So density of alkanes is proportional to molecular mass. Next one, alkanes are called paraffins because they are less reactive. Okay, so para here means less and affinity here. Okay, so less affinity means they are not attractive towards other compounds, so means less reactive. So less affinity, so less reactive. So paraffins, if in any question it is mentioned that which particular compounds are considered as paraffins, and if alkane is the option, you will select that one.